So, is it visible? Okay, so now we'll discuss about the stability. So the stability is a very, very important concept in the time domain analysis of a system. Okay, so if the system is said to be stable if it satisfies the two conditions. Okay, what is then the system is excited by a bounded input. The output must be bounded. Okay, so here this is a proof for the system. So C of t is equal to the inverse convolution of your g of s into r of s. Okay, so using the relations, convolution integral, and impulse response of the system, so your C of t must be well within the bounds for a given input. Okay, so this is for input r of t minus c any value, g of t is your system. So these values must be bounded for given inputs. Then your output is going to be bounded. So if this output is bounded, the system is said to be stable. Okay, so here this is the exact equation here, and then the second statement for the stability is in the absence of the input, the output tends towards zero, irrespective of the initial conditions. If there is no input, okay, your output must be zero. Okay, whatever may be the initial condition, then the system is called asymptotic stability of the system. Okay, so these are the important points. Now, just you observe the responses here when the roots are on the negative real axis. These two roots are unequal. In this overdamped system, your response will be bounded. Okay, so here you are observing that this response is bounded. And also for the critically damped case, the roots are equal and real. Okay, and they are having the negative real parts. These two are having the negative real parts. Okay, so this is the real axis, this is the positive, okay, and this is going to be the negative. Therefore, if any root or pole which is having the negative real axis, then the system is going to be stable. If the roots are placed on the imaginary axis, so here real part is 0, it is only an imaginary part. In previous case here, this is underdamped case, the roots are complex conjugate and it is having the negative real part. Okay, so this is the real value and this one is a imaginary value. Okay, and here the roots are imaginary only, and therefore your response is oscillatory. Okay, and now if you observe the roots with the positive real parts, okay, so your response is going on increasing. Okay, so it reaches to infinite, so there is no bounds. And here also in the second case, the roots are which are located like this. Okay, so your response is increasing towards the infinite. As time tends to infinity, your response goes to infinite. So this type of systems are called as unstable systems. So that means any root which are located on the right half of the S-plane, then it makes the system to be unstable. Okay? Therefore, here in the first case, all the roots are located on the left half of the S-plane, and therefore your system is stable. Okay, and in the second case, some roots are located on the left half of the S-plane, and some roots are on the imaginary axis. So this type of systems we can call it as a critically stable systems. Okay, and here there are multiple roots which are located at the origin. Then directly you can say that the system is unstable. If any root which is located on the right of the S-plane, then also you can say that the system is unstable system. Okay. Then, the Rao-Hurwitz criteria, it is method used for the finding the stability of the system. So it says that Rao-Hurwitz criteria says that the number of roots of the characteristic equation with positive real part. So with positive real parts are equal to the number of sign changes in the first column of the Routh array. Okay, so we need to found the Routh array. Okay, and here there are in the first column there are number of sign changes, positive, negative, positive, positive, negative, like that. So here there are number of sign changes. So these sign changes are nothing but the systems with the positive real parts. The roots with a sigma plus or minus j omega. Normally it should be always negative. Then the system is stable. Okay, so if a roots are having the negative real parts and plus or minus j omega, then the system is stable. If this is a positive real part plus or minus j omega, then the system is unstable because this real part is located at a positive value. So it is a positive real part. So the system is unstable. So we can estimate that how many roots are located on the right half of the S plane for the system. Okay, so that can be obtained with the help of Routh-Hurwitz stability criteria. Okay, so here directly we will go through the system. Okay, so here this is the Routh-Hurwitz stability criteria where I need to find out value here. Okay, so this is a Routh-Hurwitz stability criteria forming the Routh array. So this is nothing but your Routh array. Okay, so this can be obtained by taking the characteristic equation. So this B of S is nothing but it is a characteristic equation. So it is having the characteristic of a(n) s power n plus a(n minus 1) s power n minus 1 and so on plus a1s plus a0 is equal to 0. So this is your characteristic equation. With the help of this characteristic equation, we can form the Routh array. Okay, so directly we need to take the s power n. Highest power value will be taken here, s power n. Okay, so this is s power n, and this is going to be s power n minus 2. This is going to be s power n minus 4. And then the next row will be with the values of s power n minus 1, s power n minus 3, and s power n minus 5, and so on. So here these values should be represented with the first two columns, first two rows. Okay, and after that we need to calculate bn minus 1, bn minus 3, bn minus 5, cn minus 1, minus 3, minus 5, like that. These values should be estimated. So I will give you the problem here directly so that you can easily find out. Okay, so yeah, so first of all I will take the s power 4. So this is your characteristic equation. So we need to consider here s power 4, and then the coefficient of this s power 4 is a4. So here I will write a4. Then I will leave the next term. I will consider s power 2 term. So this is going to be a2. Then I will leave it. Then I will choose another term, which is a0. Okay. And then next what we have to take is s cube term. S cube coefficient is a3. So a3 we have to take. Then leave the next one, a1. A1 we should take it. Then the other one, there is no term, so we should take it as a 0. Okay, so first of all, we need to write up these two rows. Once you get these two rows, then you can calculate s square. Okay, s square is nothing but a4, a3, a2, a1. This is a determinant of this. So a4, a3, a2, a1, but this should be taken as a minus. Okay, so this will give you the value of p1. The next a4, a0, a3, and 0. So we need to leave this row. Then we need to take up this one, a4 into 0 and a3 into a0. So this value is going to be b2. Okay, and third one, there are other zeros here, so this is going to be 0. Once you get this b1, And then next you have to take s power 1. So this value a3 and b1 you have to consider, a1 b2 you have to consider. Okay, a3 b1. So here a3 b1, then a1 b2. So you are going to get the c1. Okay, next these two values are zeros, so this is going to be 0. So like that you have to proceed up to s power 0 term. Okay, so this is nothing but the route table. So this is known as route table. So this is the way of forming the route hierarchy. Okay, so for this problem, the method 1 here, we use find the stability of the system, find the stability of the following system. Okay, with the using the route service criteria. So I will directly write the transfer function. T of s is equal to g of s by 1 plus g of s into h of s, and g of s is given as k by s into s plus 1. Okay, so this is divided by 1 plus k by s into s plus 1. You are going to get a transfer function of k by s square plus s plus k. But the denominator value is called as a characteristic equation. So s square plus s plus k is equal to 0. Okay, so delta 1 is the 1. Okay, this one. And next delta 2 is equal to 1, 0, 1k. All the values are greater than 0, so the system is stable. This is the method 1. And using the route hardness criteria for the method 2 here, this is the method 2 we have discussed here. This is the characteristic equation. So you need to take up s square, s power 1. Okay, s square coefficient is 1, and next term will be k. Okay, and as this is 1, the next one will be 0. Okay, then you have to take like this, 1 into k, and this is going to be s power 0, 1 into k minus 1 into 0. This is going to be minus. Okay, or you can have a determinant of k 1 0. So 0 minus k. So this value is going to be k1. Okay, so AD minus BC minus of 0 minus k. So this value is going to be k. Then, so first of all, you can calculate in this manner also. Okay, so for the system to be stable, the value of k must be greater than 0. Okay, so this is the problem. Then there are three different cases. So the first one is no element in the first column is 0. No element in the first column is 0. And the second case is there's a 0 in the first column, but some other elements of the row containing 0 in the first column are non-zero. And the third case is entire row is 0. Okay, so here if you are taking it as s power 5, s power 4, s cube, s square, s power 1, and s power 0. Okay, so let us assume that 5, 4, 2, okay, 4, 3, 1. So this is the value. Then you can estimate S3. Okay, so 20 minus 15 by 4. So 5 by 4. 8 minus 5, 3 by 4. Okay, then you may see that this value is going to be 0. Okay, so this is the first case here. The first case here is, again you will get the values. So some values you are going to get here. Some 6 by 10, 7 by 10. Okay, 5 liters assume. So here if you observe this, so all elements, the no element of the first column is 0. This is the case 1. Okay, this is a case 1. And next, you may see that there is an element here. Okay, in the case 2, second case, this may be 0. This may be 0. Okay, so here you need to proceed further. You are going to get this value as infinite. because this value is divided by 0, you are going to get this value as 0, then you cannot proceed further. So that is a case 2. Okay, and then the case 3 is this element is also 0. So this row, the complete row will be 0. There are 3 different cases. We need to see these 3 different cases. Okay, so here the first element of the row is 0. No element is 0. So how can we find out this? So this is going to be S cube. Okay, the next one is S square. So S cube coefficient we have to write here. This is going to be 1. And then we have to leave this. The next element we have to write. This is a 12. Okay, and next 8 is there, so it is closed. So next S square term, this is going to be 6. Okay, and now you need to write this 8. This is 8. And therefore now we need to proceed further. S power 1. So I will take this one. This is going to be 6 into 12, so 72. So 72 minus 8. So this is going to be minus 72 minus 8. So it is 64. So this value is going to be 64 6. And this term is going to be 0 because there is no other term available here. Therefore, this is going to be 0. The next term is going to be S power 0. So this S power 0 is, this should be multiplied again. So I need to take up this. Okay. So this should be multiplied with 8. Then minus of 6 into 0. So this is your negative. Okay. And therefore, divided by 64 by 6. So this value is going to be 8 only. Okay. So this is 8. Now if you observe, any sign change is taking place in the first column. Is there any sign change in the first column? There are no sign changes. Okay, so 0 sign changes. And therefore, all the roots, here there are 3 roots are available. These 3 roots are located on the left half of the S plane. So we cannot find, the major disadvantage is that we cannot find the position, exact position of these roots on the left half of the S plane or right half of the S plane. But we can see that how many number of roots can be located on the left half of the plane and how many roots are present in the right half of the plane. So this we can observe that with the help of this only you can say that the system is stable or unstable. Okay. So here this is the Rouse stability table. So with that, since there are no sign changes, so there are no sign changes in the first column or outer array, it means that all the roots of the characteristic equation has negative real parts. Hence, the system is absolutely stable. System is stable. Okay, so the system is stable. So this is the way of finding the outer array and to find the stability of the system. Okay, then take up the second problem. So here S cube S square, and where here there is a sign change, so positive to positive, so positive to negative, one sign change, then negative to positive. Okay, so this is a sign change 1 and this is a sign change 2. Therefore, the 2 sign changes in the first column, so the 2 roots are available in the right hand side of the S plane. So the system is unstable. Okay, so here again I will consider this. Now this is S cube S square, so S cube coefficient is 1 and another term is 3. This is K, so 1. Okay, this is 3, this K. Then next this is 3, next 1 0. Okay, so S power 1 is, so 3 into 3 9 minus 1, so 9 minus 1, so So this 8 divided by this 3 value. Okay, and next one is 3 into k minus 1 into 0. So 3 into k by 3. So k, then s power 0. Oh, sorry. So this value should not be taken like this because. Okay, so here this is a constant value actually. 1 plus k is a constant value. So 1, 3, and this is going to be 1 plus k. So this value is 1. Okay, so this is going to be 9 minus 1. So 8 minus k by 3, and this is s power 1. So s power 1, and next s power 0. So this is going to be 1 plus k. So this is a stable. So what must be the value of k so that the system is stable? So that means here 8 minus k by 3. So 8 minus k must be greater than 0. Okay, and 1 plus k must be greater than 0. So the range of k you can find out. 0 less than k less than 8. This is the range of k for the system to be stable. Okay, so ilage meru problems cheyandi. There are some more problems. Okay, then the second method, second case here with a 0 only in the first column. So you can use the epsilon method. So in a 1000 level, just you go through the epsilon method. Okay, so epsilon method is nothing but, so whenever you are getting a 0, it should be replaced by epsilon. Okay, so s power 5, so 1 is there, 1, 2, okay, 11. So 1, 2, 11, this should be represented in the first column. Then 2, 4, and 10. So these are represented in the second column. And because of this, this is a 2 plus 2 into 2, 4 minus 4. This is going to be 0. Okay. And next, 2 into 11, 22 minus 10. Okay, 22 minus 10. So 12 divided by 6. So this value is going to be 6. Okay. Then as this term is 0, then what we have to do is 0 into 4 minus 2 into 6. So 0 into 4 minus 2 into 6 divided by 0 we have to do. So this value is going to be infinite. Then, so you cannot proceed further now. Okay. So to avoid that, what we'll do is just we consider that this is epsilon. Okay. So epsilon, and we write this value as C1. Okay. Next one is 0 into 10. So 0 into 10 minus 0. So this value is going to be 0. And therefore, you are going to get the values of C1 and the D1. So these values will be like this. Okay, instead of finding C1 and D1, directly you write here. Directly at this point C1, 4 into epsilon minus 12. So 4 epsilon minus 12 divided by epsilon. Just you write here only. Okay, and then epsilon into 10 minus 2 minus 0 divided by epsilon. So you are going to get the value of 10. Okay. So like that, you proceed and finish the route table. And after finishing the route table, just substitute for epsilon tends to 0. Substitute in the equation epsilon tends to 0. Okay. So here, this value, as this is going to be 0, this value is going to be minus. Okay. So this may not be infinite, but it is a negative. The sign is infinite. And here, as C1 is minus and this is a minus. Okay, so C1 is also minus value and this is also minus. Minus of minus, this total will be minus divided by minus. So this will be plus. Okay, and therefore you can see that there is a sign change from S3 to S square, and again S square to S1. So this is a one sign change, this is a two sign change. So there are two sign changes, and therefore the system is unstable. Okay, in the next problem also, you need to see that C1 is going to be minus, C1 is going to be minus value. So this is a minus, this is a plus, and this is a plus. Okay, so this is plus, this is plus. So again, there are two sign changes, S square to S1 and S1 to S power 0. There are two sign changes, therefore the system is unstable. Okay, so like that, we need to proceed and solve these problems on this Nyquist, Routh-Hurwitz criteria. Okay, so this is also one more problem. Just try to solve this because I will share you this video. Just try to solve these problems so that you can understand the concept very easily. Okay, so here they are taking that E is positive. So how many sign changes are taking place? If E is negative, how many sign changes? So always just you see that positive to negative and negative to positive. There are two sign changes. If you consider epsilon as negative also, so positive to negative here, negative to positive. Again, two sign changes. Okay, so there are no change in the sign changes if you choose any particular value for epsilon. Okay, so if there are sign changes are available, then the system is going to be unstable. Okay, and reverse coefficients on a constant level. This, if you want to see, this is also see reverse coefficients means these coefficients will be written in reverse value. So 3, 5, 6, 3, 2, 1. Okay, just they are reversing the coefficients, then directly you can find out. Okay, ఒకవేళ కనుక మీకు 0 వచ్చింది అనుకోండి, just you can also do in this manner that these coefficients will be written in the reverse order. Okay, so 3 s power 5, so 5 s power 4, 6s cube, 3s square, 2s plus 1. S power 5 coefficient is 1, so this coefficient should be written 1. Then you write the Routh table, then also you will get the two sign changes. Okay, so this is also used for finding the stability of a system when you see that any element in the first column is 0. Okay, and the third case, when entire row is 0. Third case, when entire row is 0. So that means here, now for the given problem, s power 6, so the coefficient is 1, 4, 5, 2. So 1, 4, 5, 2. So we are writing like this, 3, 6, 3. Okay, so 3, 6, 3, 0. Then s power 4 value is 3 into 4, 12 minus 6. 12 minus 6. 6 divided by 3. Okay, so it is going to be 2. So this value is 12 minus 6 by 3. And here 3 into 5, 15 minus 3, 12. So this is a 12 by 3. So 15 minus 3. 15 minus 3. So it is going to be 4. Then here 3 into 2, 6 minus 0. So 6 by 3. So 12. Okay. So 2, 4, 2, 0. Then next s power 3 row we have to write. So this value is going to be 2 into 6. 2 into 6, 12 minus 12. 12 minus 12. So this is going to be 0. And next one, 2 into 3, 6 minus 3 into 2, 6. So this value is going to be 0. Okay, then 2 into 0. So these values are zeros. So you are observing that this s power 3 row is going to be 0. It is of all zeros, and therefore you cannot proceed further and therefore we can assume that s power 4 as an auxiliary equation. Okay, so this is considered as a auxiliary equation. Then we need to take up this as a of s. A of s is equal to the quotient 2 s power 4, 2 s power 4. Then 4 is there, but it is s square term, not s cube. Okay, because we are leaving one term, so it is going to be s square, 4 terms of s square plus 2, this one, 2 s power 0. Okay, 2s power 0. And therefore, this is your equation, auxiliary equation. And this auxiliary equation is derived with respect to s. Okay, so d by ds of a of s, then you are getting a values of 4s cube. So this will be 4s cube plus 4s plus 0. So 4s cube plus 4s. Okay, and these coefficients of 4 and 4 should be substituted instead of 0 here. Okay, 4 and 4 should be taken for the s cube. Okay, so just those are replaced here. S cube, we are replacing this with 4 and 4. Okay, then we will proceed for the s square term. So 4 into 4, 16 minus 8. 16 minus 8. So this is a 16 minus 8 by 4. So 8 by 4, it is going to be 2. And similarly, 4 into 2. Okay, 8 minus 0. Okay, so divided by 4. So 8 minus 0 by 4. So this is also 2. So this is 2. Then again you are getting one more row with all zeros. Yes, you are getting one more zero with all zeros. And again, therefore you have to take the above equation as an auxiliary equation again. Okay, so this is the a dash of s, and these coefficients are 2 into s square plus 2. 2s square plus 2. Therefore, again, we need to differentiate this equation with respect to s. So this is going to be 4 into s. This term is going to be 0. So this value should be replaced by 4. So s power 1 so will be replaced by 4. Then we need to redraw the table. Route array will be again redrawn. Okay, so once you read on this, here this is the 4, s power 4, this value, this 4s can be replaced here. Now we need to proceed for s power 0. Okay, so 8 minus 0 by 4, so you are going to get 2. Now if you observe this first row, if you observe this first row, is there any sign changes? There are no sign changes. Okay, no sign change, hence no root is located on the right half of the S plane. Okay, but the no sign changes indicates that no root is located on the right half of the S plane, but a row of all zeros occur and the system may be marginally stable or unstable. Okay, so here S cube term we are getting it as a 0 0. So this indicates that, okay, so here this one or this one, these are indicating that the system may be marginally stable or unstable. Okay, so when we say that unstable, it is that when the repeated roots are located on the imaginary axis, then the system is unstable. Okay, if the roots, this may be located like that. Okay, so on the imaginary axis, this system will be marginally stable. If there are repeated roots on the imaginary axis, then this system is said to be unstable. But if the roots are not repeating on the imaginary axis, the system is marginally stable. So that can be obtained by using our auxiliary equations. Okay, so if you go for the auxiliary equation, there are 4 poles are available, and out of this, one pole is located at the plus or minus j, and another two poles is also plus or minus j. So that means here this is a plus or minus j, and this is also plus or minus j. Okay, so this is a negative value. So there are two roots, minus j square, and this is a plus j square. There are two roots which are available, and therefore the system is unstable. Okay, if the roots are non-repeating, then the system is marginally stable. Just you remember, the roots are not repeated, then the system is marginally stable. Okay, so for this problem also, you are going to get zeros. Okay, so here is the given system. Then we are finding s power cube. So s power 4 equation will be taken as an auxiliary equation. And next I'm getting a s cube terms. So this is your table. All the elements in the first column. So all the elements in the first column are here. Positives. There are no write-off of the S plane. But 0 indicates that the system is marginally stable. The system indicates the marginally stable. Okay, and these are the problems uh, which are to find the value of k. So for the system to be stable, what must be the range of k? Okay, so we need to find out. Okay, so this can be obtained like this. Okay, so different problems. You try to do these problems. If you have any doubts, you can ask. Okay, so this is for the route Harvard criteria. Okay, just I'm closing here. If you have any doubts, you can ask me now.